So now we're going to find the surface integral of a vector field. And this is going to turn out to be a flux integral. Circulation integrals don't make any sense really in this context, so we're going to have to think about it in terms of flux. Now the surface integral, the double integral over the surface of f dot n ds, where n is either going to be the upward or downward normal. So we're actually going to have to choose every time. You can only do one. It's going to measure the flux of the vector field across that surface. Right, it can be evaluated on the vector field f equals fgh on an explicitly defined surface z equals z of xy by the following. So this is flux. Right, the flux is equal to the double integral over the surface of f dot n ds, which is the double integral of negative f z sub x minus g z sub y plus h dA. And in practice, we can find it also with the double integral over the region of f dot n dA. R is the projection, it's the region, a projection of S onto the xy plane. So this is the region of integration. S is your surface. And again, all of this is written in the xy plane assumptions, but of course that does not have to be the case. You could do it with other assumptions if you wanted to. You could make it the surface be a function of y and z or the function of x and z. Now, the n vector is a non-unit normal vector. So it doesn't have to be a length of 1. I mean, it can be a length of 1, but it doesn't have to be. But you have to choose that direction. So what are the choices? Well, if you defined your level surface W, right? So W can be defined one of two ways. So you can define W as z minus z of xy, in which case your normal vector would be the gradient of that W1, which would be your upward normal. That's because we put the z in the front there. Now, if you put the z in the back, then when you find the normal vector, it would be the downward normal. So this integral right here, all of this up here at the top, right, that will find our flux. Now, just to get a picture of what's happening before we head off to an example. So you have some surface sitting in a vector field. And what you're trying to do is measure how much the vector field is pushing upwards through the surface. Or you could do downwards through the surface. The one I've drawn in particular is very useful for upwards. There, I just wrote that out. So the flux integral is going to measure the amount that the vector field is passing through that surface. Now, what the amount is measured in kind of depends on what you're talking about. Is this a vector field of fluids? Is this water? Is it liquid mercury? What are we talking about? Or is it heat? Or is it electricity? You know, what is it? And so that would affect what the units of this would be. But it's essentially how much that vector field is pushing through that surface. And it would be per some unit of time, right? Now, passing through, we will deal with this in terms of either upward or downward direction. For any particular spot on the surface. All right, so let's look at an example, because this is all well and good, but we have to see how the problems actually work. So we're going to find the upward flux of the radial field xyz, which is actually the field I was graphing on the last one. But we're going to look at the portion of the hyperboloid z equals the square root of 1 plus x squared plus y squared below the plane z equals the square root of 17. And of course, I just graphed that in Maple, so I had some sense of what this looks like. There's the one from the previous page, and here it is. So it's a hyperboloid, it's a piece of it, and we're graphing that, and then it's going to have some shadow that it casts down below on the xy plane. We're not going to draw the arrows of the vector field as we draw these, because that's just a recipe for disaster. So we just want to kind of think about the hyperboloid. Okay. so let's draw the hyperboloid. We could see that it was intersecting at some value, right? Because if the x and the y were 0, it would be 1, right? So it's hitting at 1. And then it's going up, so it makes kind of a bowl shape. And then the z-axis is going here. And then, of course, it's hitting at the square root of 17 on the z-axis. So this plane is hitting at the square root of 17. All right, so now we can see that it casts a shadow down below. This is the surface up here, right? And now we want to look at the shadow that it's casting, which is the region. All right, well, I drew it on the maple, but how did I get that? Well, I want to know where these two are going to be equal to each other. So to find r, I need to find the intersection. We've been doing this a long time. You set the two z's equal to each other. So the square root of 1 plus x squared plus y squared equals the square root of 17. So therefore 1 plus x squared plus y squared equals 17 if we square both sides. Squared, squared. And then we get x squared plus y squared is 16, which is a circle. So we can imagine we're probably going to be switching into polar here. And we are. All right, so our region, because it's a circle, it'll be easier to deal with in polar. Now, if you're asking, why not cylindrical? That's because these are double integrals, right? Not triple integrals. So the region of integration is right here. It's a circle of radius 4. All right, lovely. So let's kind of segment our paper off just so we can keep all that separate from everything else we need to do here. Okay, now before we start tackling this integral, we know that to find the integral, we're going to need to do some work. Namely, we need our normal vector, we need our vector field, and we need, right, this z sub x, z sub y, we need w, we got a lot of work to do. Okay, so let's find the w and then therefore find the normal. Let's start with that. Okay, so finding our normal vectors. So let's do that. So remember that z is equal to the square root of 1 plus x squared plus y squared. Sure. So w, because I'm looking for upward flux, right, w is going to be z minus z of xy. So z minus z of xy, which is what this was. I should have written it that way, sorry. That's what I meant to do. So z of xy is right here. So w is z minus the square root of 1 plus x squared plus y squared. This is our level surface. And we chose this one because we wanted upwards. If we wanted downwards, they would have been backwards. The minus z would have been in back. All right, so the normal vector would be equal to the gradient of w, which is, if you remember gradients, wx, wy, wz. All right, so the derivative with respect to x, remember that this is to the 1/2 power right here. So you bring the 1/2 down. The derivative of z is 0, so that's not going to do anything. So 1/2 down, so it becomes negative 1/2 times 1 plus x squared plus y squared to the negative 1/2 times the derivative of the interior, which is 2x. Then you're going to do that again for the y component. So it'll be negative 1/2, 1 plus x squared plus y squared to the negative 1/2 times 2y. And we didn't leave a lot of space for z, but luckily we don't need to because the derivative with respect to z is 1. That's because it's upward, right? That's how you can tell if you did it right, because upward will have When you take the derivative, it'll be positive 1, right here. All right, so let's clean that up just slightly. The 2 and the half will cancel, and so it'll be negative x over, right, because this is negative power, so it's over the square root of 1 plus x squared plus y squared, then negative y over the square root of 1 plus x squared plus y squared, and then 1. Wonderful. All right, now we need to find our vector field. So let me just put that in here. Find vector field F. Well, that's no big deal, except if you'll notice, we want x and y. We have to have a double integral, right? If you remember the problem here. So we need a double integral. We can't have 3 variables. There can only be 2 variables, right? So we're going to need to be able to find z, right, in terms of, so let's say this, in terms of x and y only, in order to make this work, in order to make the double integral work. If it was a triple integral, we'd have no problem. So the vector field was x, y, z. We can't use the z. So we have to write that as x, y, and then z was the square root of 1 plus x squared plus y squared. All right, now we're ready to find the flux, sort of. The flux would be equal to the double integral over the region of f dot n dA. Okay, so that's the double integral over the region. F is x, y, square root of 1 plus x squared plus y squared. And we're going to dot product that with, oh, hold on, I don't have room. I gotta write it right below. 1 second. I still didn't really have enough room, but I just managed to cram it in there. So there's the dA right there. Okay, so we need to take the dot product of all this, and of course we don't even have our limits of integration yet. We gotta deal with that, but let's hold off on that till a little bit later. Now I could switch to polar at this stage, but I don't think it makes anything any easier. We actually have to do some algebra work here. So we're going to take the double integral over the region, and I'm not even going to bother to find the region yet because I know I'm going to use polar. X times negative x would be negative x squared over the square root of 1 plus x squared plus y squared. And that's added to negative y squared over the square root of 1 plus x squared plus y squared. But you'll notice those have the same denominator, so I can just put them together, right, using my algebra skills, right? So x squared over this minus y squared over this, plus, now this last term will be the square root of 1 plus x squared plus y squared. Now, they are not like terms. This is over 1, right, because it's times 1. So you can probably guess where I'm about to go with this. I'm going to multiply this one by that common denominator. 1 plus x squared plus y squared over 1 plus x squared plus y squared. Square root, sorry. 1 plus x squared plus y squared. dA. So I'm doing a little bit of algebra inside my integral. All right, so then that would be the double integral of, okay, what's going to happen here? The denominators will both be 1 plus x, the square root of 1 plus x squared plus y squared. This will be negative x squared minus y squared plus, and then over here I'm going to have the square root of 1 plus x squared plus y squared. And then this will be 1 plus x squared plus y squared. And then look what happens. Negative x squared plus an x squared. These are like terms, right? So these are going to cancel, and these are going to cancel, and I'm left with 1 over that, right? Because they combine together. So this will be the double integral over the region of 1 over the square root of 1 plus x squared plus y squared. dA. Now, at this point, I need to find my limits of integration and do my integral. I could leave it in rectangular coordinates. I mean, we have done that before, but we know that a circle like this will be much easier with a polar form. R goes from 0 to 4, theta goes from 0 to 2 pi. So all we have to do is switch over 0 to 2 pi, 0 to 4. This will be r over the square root of 1 plus r squared, right? Because x squared plus y squared is r squared. And r, well, let me write it as 1, just so you can see it. But it's 1 on the top, but then you multiply by r, dr d theta. There's no theta anywhere in this problem, so we're just going to put 2 pi here. And we're going to take the integral from 0 to 4 of r over the square root of 1 plus r squared dr. And of course, we are going to make a computer do that for us. Please and thank you. So let's go look at it in Maple. And there we can see it in Maple. There's the exact answer. Right, here's our surface right here. And there's our exact answer, and there's our decimal approximation. So I just wrote those values in right here. Equals this, but then is approximately that. And we don't have units because we're not sure what our context is. We don't know if this is electromagnetism, if it's heat, or what we're looking at here. So we would need to know units for the vector field before we could come up with a unit for this response. But whatever it is, it would be some unit per time, right? Because the flux is measuring how much is passing through the surface per unit of time.